option. Let me just try it. Does it give you something like a prompt that somebody's trying to record?
It says it's recording now, so it is currently recording.
Yeah, so I'll keep it, and I guess you can edit this part or even keep it. So.
All right, well, so what happens is if you're recording, you will need to be the one to upload it to YouTube. Does that sound good? Okay, I'll send you the instructions for how to upload them and like what to put in it.
Yeah.
All right,
no problem.
So I'll go ahead and let people in, and I'll turn off my video, but I'll be around if you need me.
Sure. And as I said, since I'm recording, once I'm done, it will convert and all that. So don't worry about that. Yeah.
Awesome. Sounds great. Thanks so much for doing this at the last minute as well.
Yeah, no problem. I mean, my pleasure. Yeah. Okay, so
Rahul, before we get started, also just about the recording, can you make sure that the thumbnails of people's images aren't blocking the recording screen?
Yeah, so I keep it like this. Like, do you see it? So since my screen is shared, so it's minimized. There are no thumbnails. Yeah.
Sounds good.
Yeah. Okay. Hello, everyone. Welcome to the homework review session again. We'll be starting at 4, so we have 1 minute now. I hope everyone had fun doing homework this week. These are the homeworks. So again, as I said, like if I had infinite time, I would just sit here and keep doing homework. But since we have finite time, our goal is to make sure that we go through all the required problems. Optional problems we don't usually discuss in this session. If we get time, we will definitely discuss them. But the goal is so that everyone is on the same page. All the students are comfortable with the required material. So we'll spend more time and hopefully try to go slowly over all of them. So. Okay, so I'm blocking the chat for now. I will reopen the chat when I ask for questions, or actually I might even ask you to raise hands and ask questions in person. So we get to hear some of your voices. That would be nice. Okay, so chat is stopped. Okay, so it's 4 p.m. now. So hello, everyone. Welcome to another homework review session. We'll go through each problem, maybe discuss a few concepts. And yeah, I mean, generally the idea is to have fun. So we have 4 problems. I think so last time I went over time and I respect people's time a lot. And so this time I'll try to finish on time. So I'll try to devote 15 minutes on each problem, roughly. So if we have some leftover time, we can discuss some other things as well, if you guys would like. Okay, and hopefully finish everything by 5. So welcome everyone again. It's Deepavali in India, so happy Deepavali to everyone. It's a festival of victory of light over darkness, and I guess in most cultures, people associate light with knowledge and darkness with ignorance. So it's victory of knowledge over ignorance. And hopefully after this session, we would have increased light in our life and removed some of darkness. So that's okay, cool. So let's start 401. So the first problem is the inner product is a measure of closeness of 2 vectors. For vectors A and B, the inner product is given as, they have given this notation. Compute the following inner product. Okay, so let's discuss what an inner product is. First, let me try to remind you of some definitions. So what is a vector? I know most of you know, but I'm just repeating. By the way, if you were here last time, there are educational research that if you speak with somebody who is teaching you or somebody who you're talking with, then you retain more and your brain becomes sharper. Basically, there is research on that. So I know it's somewhat childish to shout answers, but it does help. So when I say shout, or when I'm leaving, prompting you to say something, please say it at your homes, and I think it will help all of us. So So vectors represent two quantities, which are magnitude and direction. So vector represents two quantities, which are magnitude and direction. So let's write them down. I'm not super skillful with my pen, so sorry about that, but I'll try to do as best as I can. Right. So vectors represent these two things, and we represent them by arrow. So we draw this arrow, and so magnitude is basically the length of arrow, and direction is basically you pick one reference line. Let's call this x-axis. Then this angle is the direction. Oh wow, today is particularly bad. Anyways, no problem. Direction. Okay, so right. So what does inner product mean, right? So again, I'm going to talk about the physical meaning of this thing, but I will not necessarily prove things. So for that, I encourage and I invite you all to try it on your own. But let's see what inner products are, right? So the prompt says in the homework that they are measure of closeness between the two vectors. But what do we mean by like closeness, right? So let me give you an example, and in fact from your course, right? How nice is that? So let's talk about, let's say, light, since it's Festival of Light. So I'll talk about light. So light is, I mean, everything in the world is quantum, although we don't see it on larger scales, but on smaller scales, everything is quantum. So light has a quantum property, or on larger scales, it's a classical property as well. It's called polarization, right? By the way, as I said, if you don't get any of this discussion, don't worry. Like homework, as I said, all the problems will be solved with homework. This is just to motivate. Like, why do we even care? Why are you sitting with me, wasting time on a Friday or Saturday morning? Depends on where you are, rather than doing something fun, right? So let's look into it. Why I'm boring you guys right now? So light has a property called polarization. It just means that. So if you think of light as a wave, then which plane the light is oscillating in. So if you look at this wave, like light is oscillating like this, and you can tilt this wave slightly. If you tilt this wave, then it's oscillating in another plane. So basically light can have any of these polarizations. So why does this matter? So first thing you notice that these are all vectors, right? Okay, so this is just an example of vector. Light has a property called polarization, which is a vector. What is polarization? If you understand, great. If you don't understand, just think of it as some property. So that's for waves. But again, we have not discussed quantum mechanics, but you will discuss later that light also comes in packets, which are called photons. So photons also have this property. So they also have polarization like this. Anyways, actually, I shouldn't have said that word. Forget I said that. So light has polarization. Okay. What does this have to do with inner product, right? So the concept of inner product is, it goes like this. You have a vector, let's say. The vector is like this. I just showed you that vector is arrow. Remember, vector is magnitude plus, all of you say with me, direction. Vector is magnitude plus direction. Okay. So and it's represented by an arrow. So let's say this is your vector and it's a quantity you want to measure. It's a quantity you want to measure. Let's call this vector Q, right? Now, how do you measure something? To measure something, you need some sort of detector, right? So let's say you have detector. I'll come back to light. So you have a detector. So you have a detector, and detector, if it has to measure vectors, right? If you want to measure something which is like an arrow, then your detector also needs to have some sort of direction defined, right? Like if you want to measure a vector quantity, and vector is again magnitude plus direction. So detector also will have some direction, some axis along which you will measure things. And so what inner product tells us that if you measure So let's call this vector D, and let's call this vector Q. Well, I already had the hat on it, so no need for double hat. So, okay. So Q and D, right? So you want to measure Q in D, and you can see that the directions are different, right? Like they're not pointing in the same direction. So the result you get, if you measure these, if you measure, the result you get is going to be proportional to Q dot D. That is the meaning of inner product. And how this works, let me just draw a very simple figure. So you have your detector D here. Let's bring this vector, on its tail here. Let's join the tail. So this is Q. So if you have a detector here, it's kind of obvious as well. If you think about it geometrically, try to be a kid again and, think simple, don't think complicated. Then if you have something which is measuring something here, and you have something which is pointing something here, what it will measure, actually, let me draw a different color. So you just drop a perpendicular here and basically drop this arrow down. So when you drop this arrow down, by the way, dropping arrow down, not like a circle, but you take a perpendicular component, you drop it here. So this length is what is in technical terms called projection, first of all. So I hope all of you have notebooks and stuff. So you can write down this keyword. So projection is a keyword. Projection is a keyword for you. So you do projection, and this length, the magnitude is called projection, and it's a scalar. You can see that there is no arrow here, right? It's just a length. So this is basically Q dot D. That's the inner product, right? So in case of light, so I don't know how many of you have seen polarizing filters or like sunglasses, which use these polarizing filters. So this is just an example of how this works in real life. So if you have a polarizing filter, I told you that light comes with all these vectors at you. The light which is coming from sun has all these vectors. So this is your quantity Q. And your detector for a polarizing filter has a particular direction. Sometimes these things are called axis, so it has one direction. And when you measure it, you can see that only some of the light passes, right? Like some light which is perpendicular to it will not pass. So when you measure it, what you get is Q dot D. And and this value is and this value is going to be less than Q. That depends on what kind of filter you are using. But I'm just telling you that this is a practical use, that you set a detector on an axis. If you have all sorts of light coming in, you measure it, you will get less light. So once you get less light, Q dot D is filtered light. Anyways, and like the key thing here is measurement. Right. So now we understand what inner product is. Inner product is a projection. So let's repeat that. Inner product is a projection. Inner product is a projection. And it's a scalar. It's a scalar. It's a single number, scalar. Okay, inner product is a, all of you say with me, projection. Okay, and it is a scalar. Okay, cool. So, okay, I'm already close to 15-minute marks, but I think, yeah, this is useful because we'll kill two birds with one stone. So problem 1 and problem 2 will be done with this discussion. Okay, so let's look at it again. So here we have our detector or some vector. You can take any vector. I'm just calling it D. And here I have my quantity, which is Q. Now, so as I said, so the homework says it's the degree of closeness. So what does this closeness mean? So if you have something like this, you bring it here, its tail here. So this is also Q. You drop it here, it makes this projection. So you realize that whenever this theta will be less than 90 degree, your Q dot D will be positive. By positive, I mean the length is measured along D. So I will just write it down, along D. So if you have two vectors, you take their inner product. If the angle between them is less than 90 degree, then the inner product is going to be positive. And it's not some fact, like you need to remember, you can see it, right? Like you take this vector, you take, let's say, this vector, and you can see when you drop this perpendicular, you see that it's along this vector here. And it's a length along D, so it's positive. So along D, positive. Now, what if theta is greater than 90 degree? Let's look at that. So I have D here, and my Q is something like that. Now, how do you drop a perpendicular from Q? Let's again bring it to the tail so that we can look at it. So my Q is here. Now I drop a perpendicular. Dropping a perpendicular is projection. Dropping a perpendicular is projection. If you haven't heard this word, this is just a new word. Drop a perpendicular to a vector. And okay, let me write it in clearly. So this length is called projection, but projection of what? So it's called projection of Q along D. So that's correct English way to say it. Projection of Q along D, and that is what we call Q dot D. It's a scalar number. It's a scalar number, remember. No, but now look at this. So you get this length. Okay, I know my length, but it's not along D. So it's like, so D was from here to here, right? It's not along D now. Let me draw it in a different color so that it's clear. So my projection here was this, and my projection here is now this, which is, away from D now. So the way that dot product captures this information is that if you calculate this guy, again, I'm not proving these things, but you will do some exercises and you will see examples. And if you are interested, in free time, you can try to prove this. So you will see that Q dot D is less than 0. Again, these are like, okay, so if it's along D, it's greater than 0, and along D is when theta is less than 90. Here theta is greater than 90, and when theta is greater than 90, it's opposite to D, and you see that this is going to be negative number. We'll see that. We'll do some examples and we'll see that. Okay, so now we have learned two things. One is that if the angle two vectors make are less than 90 degree, then the projection is greater than 0, which is positive. If the angle is greater than 90 degree, you can see it as well. It's sort of like, visually obvious as well, that the projection now is pointing, well, there is no pointing to it because it's a scalar quantity, but it's lying beyond D. It's not lying on D. It's lying like opposite to D, sort of. So that's why we get a negative number. So, okay, so now if I told you something gives you negative and something gives you positive for this range, then all of you, I guess, can guess what lies between negative and positive. All of you say at home, what lies between negative and positive? It is 0. Yay. So if my D is like this and my Q is like this, right? Then if I drop a perpendicular, let's do it in a different color, blue. So if I drop a perpendicular, it will just follow this line, right? I'm just like drawing it slightly away, but it's just here. What is the length here? There is no length, right? Like I'm just, because you drop a perpendicular, it just drops onto D, and like there is no projection. It's like 0, right? So that tells you that when, okay, go back to black. So when theta is equal to 90 degree, then Q dot D is equal to 0, right? So this also tells you, again, remember the measurement thing as well, because in quantum mechanics, what you will do, I gave you a light example, but in quantum computation, just to relate stuff, Q and D can be any vectors, by the way. So in quantum computation, your Q will be qubit and D will be some sort of detector. So these are just, I'm just saying this is very useful in real life, all sorts of engineering, all sorts of mathematics. But for your course, as I said, so if somebody told you that, oh, my qubit is at 90 degrees to my detector, you don't even need to measure it. You can tell him that, dude, it's useless. You are going to get 0. And why? Because you draw this diagram and you see that if I drop a projection, it's going to be 0. Okay, that's all about inner product. Let's do a few examples, then we'll take questions. Okay, good. So let's look at your homework now. Cool. So, okay, so this was the physical interpretation. This was what an inner product means. Now, how to calculate inner product? So we have learned what inner product is. Now we are going to look how to calculate inner product. Again, so you might say that, oh, you showed me some calculation, but I don't see how this calculation is related to all these arrows you draw. So I'm just saying, take it from me, like believe it for now, and try to prove it in your own, time. If we had infinite time, we would sit down and, prove that thing. It's not very difficult. If you know a little bit of geometry, you go back to your classes for coordinates and trigonometry, draw some vectors, draw those projections, which I said. You will see that what I'm going to say here in how to calculate inner product, you will see that this exactly means what we said above. Right now, the relation might not be obvious, and that's totally fine. Okay, how do we calculate that? So let's say we have vectors and A1, A2, let's call this vector A. And there might be more. Let's call the final one AN. And then we have a vector B, which has components. By the way, these things, the small numbers, these are called components. And so B1, B2, Bn. Very simple, calculating inner product is like probably the simplest thing ever. So what you do, you just align these two vectors and then just multiply line by line. So you do A1 with B1, A2 with B2. Similarly, whatever you have down there, and then AN to BN. And the way you write it is, so A dot B. There are different notations for that. And I would ask you to not worry about all of them. Well, I come from maths, I come from physics. So in my brain, everything is a quantity. Like as I explained above, everything has a physical meaning. How it's written on paper, how it's written in different cultures, how, different instructors write it, that's basically not my problem. So I'm just telling you, like you just think of the thing, the reality, the truth. And then how people write it, it's fine, So I'll tell you my way to write it. So it's A dot B. Your course, people write it like A, B, like this bracket. Some people who treat them strictly as matrices, they also write it A transpose B. But again, don't worry about them. If we have questions later and if we have time, we'll do them. So, okay, so the way to do it is A1, B1 plus A2, B2 plus A3, B3. Keep doing it up to AN, BN. That's all, right? Simplest thing ever. First element to first element, add. Second element to second element, like take product and then add. So keep doing that. Okay, so now we know this. Let's solve problem 1 and 2, which are both based on this concept. So I think we'll finish around 4:30. So that's good. So which one should I do? 1 and 2 and 3. Which one is more funny? So let's take one with negative numbers, just to show you that, negative numbers also work. Like, so let's, yeah. So let's do number 3. So it's, do it with me, please. If you have notebooks, please take them out. So 1 minus 2, 4. That's my vector A. Then my vector B is 2, 3, 3. Then A dot B. By the way, as I said, physically what this means, this means that this is some vector and, I have some other vector A here. And if I'm trying to measure A along B or B along A, this is what this number is giving me. This is, so, that's what you should think about. It's like a physical picture. But anyways, if you don't understand that, it's fine. But let's, for homework purposes, and right now in the course, as I said, you will discuss these things later. But just for homework purposes, just for mathematics, the way we do it is, okay, same technique. first element multiplied by first element. So 1 times 2. Second element multiplied by second element. So, and we add, so plus minus 2 times 3. Remember to have the sign, a lot of people make this mistake. They forget the sign, but always keep the sign. Then third number with third element of A, third element of B. So plus 4 times 3. And then what is this? 2 times 1 is 2. I hope you guys are doing it with me. Sorry, I should have said that. Please do it with me. And probably you will do it before me as well. I'm slow. You guys are faster than me. 3 times minus 2 is, I'm classical computer, you guys are quantum computers, So 1 times 2 is 2, 3 times minus 2 is minus 6, and 4 times 3 is 12. 12 minus 6 is 6. 6 plus 2 is 8. I hope everyone got that, and I hope it's one of the correct answers. Yes, number B, right? So B will be your correct answer for 3. So this is how you do dot products. Again, it's very simple. Things to remember is that this is a scalar. When I did my lab, I had a poll where I asked people what is the dot product of 1, 2, and 2, 3. So let's just do it right now. Like, you guys write it down on your notebooks. I'll give you options. A is 2, 6, and B is 8, and C is like minus 8, let's say. So how many of, right? So what sometimes, if you are new to this, what you might sometimes say is that, okay, multiply top to top, multiply bottom to bottom. Sometimes people report this. Please don't do that, because as I said, it's a scalar, it's a number, it's a length. So it's just a number. So it's going to be 8. You don't write it as vector. So that's a common mistake new people make. But just remember, projection, length, measurement. Okay, and these are all scalars. Good. Second part we'll also do, then we'll stop for questions, because second part is just related. So state whether the following vectors are orthogonal or not. So I just told you, right? Recall again. If I have two vectors, vector B, let's say, and vector A, if they are orthogonal, then what have we learned? What is the length of projection? What is projection? Projection is dropping a perpendicular. So I drop my perpendicular. Oh, well, I mean, I can't find any length, like, that's so sad. Okay. So then what is the length of projection? It's 0, as you just saw by trying to drop a projection. And we know that dot product is projection. So A dot B equals, length of projection. Let me just write it down. By the way, remember that this length, sometimes it's reported negative. You might say that, oh, how is length negative? But I just told you that if the length is in this region, which is opposite to B, then it can be negative as well. So there is no contradiction there. Positive lengths fall here, negative lengths. So here A dot B will be less than 0. And if the projections fall here, then A dot B is greater than 0. So simple thing. And in between negative and positive is, you draw a real number line, you have negative, you have positive, what is in between? 0. So that is 0. So if A dot B is 0, then that implies that A is perpendicular to B. So this is the thing to remember. So if this is 0, then A is perpendicular to B. I just showed you how to do it, the dot product. So now you are all experts in doing dot products. When you do dot product, you get 0. You know that they are perpendicular. So let's do that. So which one should we do? Okay, so let's do number 4, I guess. So number 4, we are doing number 4. So it says my vector A is 1, 5. Then my vector B is -5, 1. Are they perpendicular? That's the question, right? And we just told you how to figure out. So do the dot product. So please do it with me. Do the dot product. How do we do the dot product? Top multiplied by top. So 1 minus 5. So I'm writing A dot B. And then you add. Then second one multiplied by second one. What if we had more? If we had more, we'll just keep adding those. But we only have 2, so we'll write only 2. So this is -5 plus 5. Oh, lo and behold, it's 0. So then A dot B is 0. What does that mean? That means that A is perpendicular to B. So the answer for part 4 will be that it's true. Okay. Cool. So let's ask for questions. We have 3 minutes. Actually, I mean, obviously, I'll spend probably more than 3 minutes. But so please raise hands. I'll ask one of you to speak. That would be nice and interactive. So yeah, please raise hands, and one of you I'll unmute and you can speak. Is there a raise hand feature? Okay, let me also open the chat in case you are shy and you want to just type. So okay, so let me go to chat and open it. So okay, here is chat. So everyone can chat publicly now. Yes, please type questions. What is meant with perpendicular? Perpendicular means that two vectors have an angle of 90 degrees between them. Okay, cool. Why it being 0 makes it orthogonal? I just said those things. Please watch the video again, but I'll repeat it. Okay. Can you repeat the solutions to question 1 and 2? Well, I didn't do 1 and 2. I did 4 here and I did something else. So those are okay. I'm taking all these questions into consideration. Anything more? Somebody raised hand, so I'll let them speak. My point is, how do I find them? Okay, I found him. So Anthony, you can speak now, please. And yeah, okay. You can. Yeah.
Hi. So I'm looking at number 10, and it looks like, I don't know, it has multiple dimensions or something like that. I'm not really sure how to word that.
What number 10?
Number 10. Question number 10.
This one?
Yeah. So okay. Are these going to be still multiplying A and B, A1, B1 plus A2?
So this is a matrix multiplication. This is not a dot product. We'll get to it. So as I said, this is one of the problems. We'll get to it. Yeah.
Sorry.
Yep. No problem. Yeah. Good question. Thank you. You can mute yourself back, I guess. Okay. So in chats, I didn't get many questions. So I'll stop the chat again, and then we can talk about the questions I got. Okay. So we plug the chat so that you guys are not disturbed. Okay, so the few questions we got. So somebody asked me to repeat some problems. Please let me tell you that like both problem 1 and 2, how to do them is simple. As I said, just if you have A1, A2, A3, A4, AN. This is for problem 1 and 2. B1, P2, P3, B4, however many, Bn. The dot product between these two vectors is A1, B1 plus A2, B2. I'm just repeating this thing just because some people asked, and it's not a problem. If something is new, it's like riding a bike. You always find it difficult, but later it will become super easy. So you keep adding until A and Bn. Now you do that, right? Sorry, my N is bad, but yeah. Okay, so you just write this number. That gives you problem 1. So problem 1, all the parts of dot products, you just need to do this. Take the product, first to first, second to second, third to third, fourth to fourth, and just take care of signs and then add them. This will give you problem number 1. Problem number 2, this is asking you if the vectors are orthogonal. So some people ask me, what is orthogonal? So again, don't get bogged down by all this Greek, Latin, different languages. It was difficult for me too. Orthogonal just means, so A orthogonal to B, or A perpendicular to B, or A, let me just write the whole thing. A normal to B, like these are all English things. what all of this means, and maybe in your language you have different word for that. All of this means is that if you have an arrow here for B, if you have an arrow here for A, the angle between these two arrows, and they might be at different locations, but once you bring their tail together, the angle is 90 degrees. So theta equals 90 degrees. That's all it means. Again, since I'm from physics, I just look at the image. I don't even necessarily understand what is theta and what is 90. But once I know that they have to look like this, then you have got the concept. So this is what is meant by orthogonal. That's what I would say. Independent of language, cool. Okay, so that is what meant by. So problem 2, okay, to come back to Olga's question who asked. So 2, you calculate this thing. So 2, do 1, which is calculate the dot product. And then if 0, that means A is orthogonal to B. And if not 0, if you do 1, which means you calculate the dot product, let me just say do 1 means calculate dot product, calculate A dot B. And I told you 3 times how to calculate it. I'll quickly do one more for you. 1, 2, 3, 5. Do it with me if you are doing it. So multiply this 3 times 1, multiply this plus 2 times 5, and then add them basically. So I already added them. So 3 times 1 is 3, 2 times 5 is 10, that's 13. So yeah, so that's how you calculate dot product. This is not 0. So then you would say A is not perpendicular to B. So that's how you do 2. Okay, so this will be false, just to get back to your questions thing, and this will be true. And how do you get that? By calculating A dot B. If this is 0, your answer is true. If it is not 0, the answer is false. Okay, cool. Dot products are done. Let's go to the next one. We are making good time here, thankfully. Thankfully, this homework was easy. Okay, so next one is, I like to open another version of homework as well, because do I have it downloaded? No. Okay, let's look at Google Drive, homework, assignments. So why I'm looking at that is because here they are calling 1, 2, 3, but each problem has a concept. So this concept is done, second concept is done. The third concept is linear combination. Okay, so let's look at that. What do you mean by linear combination? So okay. Right, so let's do one of them. So what do you mean by linear combination? So let's understand that first. So linear combination. Right, so linear combination, if you understood like superposition, it's like how do you create superposition? So let's go back to our example, quantum computation. That's the course we are doing, right? Quantum computation. Although this is true for all engineering, all physics, a lot of things. But let's do this example. So quantum computation, we are working with qubits. Again, if you don't understand qubits, don't worry. I'm just telling you. Let's say there are 2 kinds of qubits, right? One is 0 and like one is 1. Or if you like funny stories, let me just talk about like a cat, right? Like there can be a cat which is like dead. Well, I don't know how to draw a dead cat or a live cat, so I'll probably not try that. But so I can just write a dead cat, and I have a live cat. Actually, let's not talk about cats. This is not a very exact analogy because cats are big and quantum effects are good when things are small. So let's talk about electron spin. Again, if you don't understand spin, it's fine. You probably heard of electrons. Even if you can't think of electrons, let's think of atom. Atom is something really small. Atoms have a property which is called spin. So again, they don't rotate, but let's imagine that an atom is moving. They have a spin which is pointing up, let's say. And you have another atom here, which is moving in another direction, rotating on its axis, Like I have a rotating chair, I can probably rotate. So like that. Atoms don't really do that, but this is just to make analogy simple. So you have a spin down. Okay, so now what you want to do in quantum computation, that take these two things and create superposition. Again, if you don't understand it, no problem. You will be doing it in future, but I'm just telling you that to do quantum computation, and you might have seen this in your lecture, that you need stuff like this, right? Alpha 0 plus beta 1, something like that, right? You want to create superpositions. You want to add these two things and create something new, right? And how do you do that? So this is this problem. So, okay, so let's look at, yeah, I could give you a general formula, but I guess it's better to look at an example. So, okay, so let's look at problem B here. So, which is problem number what in the other document? It's problem number 7. Let's do problem number 7. Okay, problem number 7. So I showed you that to create superposition, you have these guys. And you do something, again, like we can talk about what you do, maybe not here on Piazza or something, but you do something with them, you do something, some magic. That magic, like most magic in the world, it's just science, you do some science with them. Can't write science, that's sad. Okay, science. You do some magic or science with them, and you create a superposition. So it's 0 and 1 at the same time, or it's spinning up and down at the same time. You can also write like alpha, up plus beta down. Again, as I said, you don't need to understand all of it, but I'm just saying it's possible to take two different quantum objects and create a superposition. So this is what this problem is talking about. So they tell us what components they have. So they tell us what components they have. So they tell us A. So this can be A and this can be B. So they tell us A and B. So where is their A and B? Okay, so their A is 1 and 2. So they say my A is 1 and 2. What is B? Their B is, oh, too many windows open. Their B is 3 and 1. So their B is 3 and 1. So think of yourself as, a supreme quantum engineer or something, like you are going to do some very fancy stuff now. So you have some fancy thing here, these two qubits, let's say, and you want to create a superposition of this qubit, which, in real life is like magic. But that's why maths is cool, because you can do all this magic on paper without, worrying about anything else. So okay, so let's try to do that magic. But so what you want to do, you want to combine these two, create a superposition, and then get what? So you can get anything you like based on some restriction. In your free time, you can think what restrictions apply. I'm not going to answer that here, but you want to create a superposition, do some magic, and get what out. So this is what the problem number, come on. Yeah, problem number 7. So problem number 7 we are doing. So let's write it down. So we are doing problem number 7. Problem number 7. You combine A and B, which means create a superposition, and you are told that what you need. So it's like your boss, quantum engineer, your boss comes and he's like, hey, whatever, X, please create a qubit for me, which is -7, 16. That's what they ask. So they come to you, they tell you, we have 1 and 2 in supply. We have 3 and 1 in supply. Can you please give me 7? What is that? -7 and 16. Can you please give me -7 and 16? So that's the question. You have a qubit 1, 2. You have a qubit 3, 1. Can you give them a superposition, which is -7, 16? Now, how do you create superposition? I just wrote down on the top. So -7, 16. This has to be some alpha times, vector 1, which is 1, 2, plus some beta times 3, 1. So superposition, let me just give you a general formula. This is always going to be some number times this number. Okay, your homework uses X and Y. So let me just write X and Y. Alpha and beta can be x and y. I just told you language doesn't matter. So x times a plus y times b. So superposition means this. Superpositions means xa plus yb. Superposition means xa plus yb. Simple. So just add. That's superposition. But you add with some weight. That's the thing. Okay. So you apply some weight x and y, and then you add them. Okay. When you compare vectors, so when there is an equal sign between two vectors, what this means is that the first component is equal to first component, second component is equal to second component. By the way, this is not advanced. If I went to a kid who didn't know about vectors, I showed him, dude, look at this. What do you think? You know, there is an equal sign in between, and you probably have heard of equal sign. What do you think is going to be equal? So if you ask them, they would probably, you know, intuitively say that, okay, you know, first guy will be equal to first guy, second guy will be equal to second guy. So it is like that, you know, it's not, don't make it too complicated. So let's do that. So by the way, in vector addition in last homework and, you know, last labs, you have learned that this is what you add these vectors, you get a new vector, x times 1 plus y times 3. So the way addition works, just to repeat, take it in and then add. So take it in, so it will be x, and then this will be x times 2, and then bottom will be y times 1. And this is the new vector. This is minus 7, 16. By the way, I hope you're doing with me. Sorry, I keep forgetting to say that. But if you have notebooks, please do it. I'm sure you are faster than me, so you do it. So okay, so now I told you how to compare vectors. So this is how you compare vectors. Compare. How do you compare? Okay, so we are comparing it. So first element is equal to first element. So we write this down. Minus 7 equals x plus 3y. And then 16 equals 2x plus y. Okay, so I've got two equations. Can I solve it? Let's name them. Let's name this 1. Let's name this 2. So to solve an equation, again, you know, I hope you know how to solve equations. I can go into it, but you know, I probably don't need to. So if you're confused, ask me later. So we do 2 minus 2 times 1. Why do we do that? Because we want to cancel our x. So when we solve two equations, we want to cancel one of the guys so that we only get the other answer. So if we do that, so let's write equation 2 on the top. So 16 equals 2x plus y. And then we do minus 2 times 1. So 2 times equation 1. So 2 times equation 1 is what? 2 times minus 7 is, let me just write this down in another step. 2 times this, then 2 times x. Actually, even to make it more clear, just want to make it absolutely clear. 2 times minus 7, this whole equation will get multiplied by 2. So 2 times minus 7 x plus 3y. This is our equation, right? And we are going to do this. So what this means, 16 equals 2x plus y. Now bring the 2 in, multiplied with everything. So it's minus 14, 2x plus 6y. Okay, and I told you to subtract these guys. So you have to subtract these guys. So there is a minus on the outside. So there was a minus outside. So if you take it in, what will it become? Plus, this is minus, and this guy will become minus. And why did I do that? Why did I do all of this? How did I know what to do? I wanted to cancel this x with 2x. And how do you cancel x with 2x? You multiply this guy by 2, and then you subtract. Then 2x minus 2x will be 0, right? So that's the logic I used. Nothing super big. I guess you know how to solve equations. I don't know why I'm going over it. But anyway, so I already took the minus in. So now we can just add. So this is 6 plus 4 is 10. 1 plus 1 is 2. And then 1 carry over. So 30. 2x and 2x, when you do, like, they cancel. Then y and minus 6y is minus 5y. So then y, you divide both sides by 5. Both sides, divide both sides by 5. So 5y by 5, 5 cancel, you get 1. And then 30 by 5. Actually, there was minus, so there is minus. So divide both sides by minus 5 maybe. So that you divide by minus 5, you just get 1. So minus 5, divide, get 1. And then 30 divided by minus 5 is minus 6. Okay, so we have got the value of y. So y is minus 6. Okay, so how do we get x? Now just plug it. So plug y equals minus 6 in. You can choose any equation. Both of them will give you the right answer. And you should check that, by the way, all the time. So let's plug it in this guy. This looks simple, right? So let's plug in this one. And what was this equation? This was number 1. So plug 6 in 1. What do you get? Minus 7 equals x, which is, we don't know, plus 3 times y. Y is what? Minus 6. So what does this gives us? So this tells us that minus 7 equals 3 minus 6 3s are 18. So then add 18 both sides. So then x minus 18 plus 18. So this thing cancels. And minus 7 plus 18. This gives you 18 minus 7 is what? You all shout. 18 minus 7 is 11. So we got our answer. X equals 11, y equals minus 6. So let's see if it's one of the answers. It is, right? Number A for 7. Okay, so your boss came to you, gave you 2 qubits, A and B, told you give me some other qubit, which is, some capital A, right? Or let's call it something else. It asks you, some Q. So can you do that now? All you quantum engineers, you can do this now, right? If somebody gave you 2 qubits, Q1 and Q2, or Q2 and Q1, came to you, told you that, dude, I have these 2 qubits, please make a combination of them and give me another qubit, capital Q. So you say, okay, I will do my magic. And what is your magic? Your magic is just writing it down as XA plus YB equals Q. This is your magic. You write your magic, solve, and get X and Y. By the way, even in research, if you are a theoretical researcher, this is your job. You just do everything on paper. If people like me who do physics, they come to you, they would be like, oh, I have these 2 qubits. Give me, how do I create, this new qubit? So what you do, you take out your paper, you do this math, and you just tell me that, okay, Rahul, this is what you need to do. You need to combine this much of A and this much of B to get this. It's like how you cook, right? Like how much of, salt, how much of sugar, things like that. So you tell me, and then it's my job to create the recipe. So, and your job is just to tell me how much of each ingredient to combine to get the final recipe. Okay, so we have 5 minutes extra, but we'll again stop for questions here. Questions on linear combination, please. So questions on linear combination, please. So I will unmute as well. And by unmute, I mean, please raise your hands if you want to speak. And I will also undo the chat so that we can hear from people in chat. Okay. So everyone can chat publicly now. Please, yeah, type your chats. If somebody is raising hands, if I see them, I will ask them to speak. Questions on linear combination. Questions on linear combination. Questions on linear combination. Any questions? I hope I'm still online. Tough calculation? If you continue with this field, you will see a lot of tough calculation. So don't worry. Anything else? Anything else? I'll wait for a minute and then I'll go to, is anybody raising hands? No. What does it mean when one of the variables are undefined? Actually, I didn't get that. Do you want to speak, Akshay? Like, should I unmute you? Like, do you want to speak? Okay, so Akshay would like to say something. So how do I unmute Akshay? Can you unmute yourself? Sorry, like, can you try unmuting yourself and speaking, please? Otherwise, let's find, yes, you are here. Yeah, so I think you are unmuted. So, yeah.
I was wondering, like, when you would usually solve out an equation like this, sometimes you get like a number equals a number. So what does it mean when you get that?
Number equals number. I'm sorry. So, like, you mean x equals y? That's what you meant, or?
No, in like a regular system of equations, if you were to solve it out, sometimes if it's the same exact equation, what does it mean? Like, it could be the same exact equation. Or like it's parallel.
I'm sorry. As I said, like if it's like I'm not getting it, sorry for my ignorance. It's definitely my fault. But please put it on Piazza, and we'll try to answer. I'll talk a little bit about linear systems, by the way. I think you raise a good point. I'll try to address it. Okay, so yeah, so you can mute yourself back again so that we don't get any disturbance. I'm closing chat. We'll discuss this point for a couple of minutes, and then we'll go to last problem, and then we'll be done. Unless you guys want to stick around, which is fine. So, okay, chat is closed now. So it's a good question. So I think the question was that if you have two things like this, x plus a plus yb, which actually, if you remember, I asked you to do it on your own. So, you know, equals q. I asked, I asked you to figure out situations where you can't find x and y. So that was a homework problem for you. But since Akshaya asked, I'll tell you. You can think of it, by the way. Think of it for 30 seconds. So you have two vectors. In what situation, if I have two vectors and I ask you to create something else and you can't do it? So I'll give you 30 seconds. Get some water. Okay. Let me just, draw things and then you'll understand probably slowly. So you have this axis. Okay, I think I gave you guys time. So let's talk about it. So I have given you two qubits or two vectors. I asked you to give me a third vector. In what conditions you can't do it? So to write down, so recall your coordinate things. To write down any point, you need two coordinates, right? Like two different coordinates. And if you remember Fran's lecture, to be honest, okay, yeah. So if you remember Fran's lecture, she probably told you, I mean, that's what I was told that she told you, I actually couldn't attend, that if you have two vectors A and B, you can write any vector in your plane using these two guys. But when you can't do that is, like if your both vectors point along the same direction. So if A equals to some lambda times B, which is to say, if this is my A and this is my B, and I ask you to create this Q, you can't do that because these guys are parallel, right? So this is another way of saying that parallel lines cannot intersect. This is somewhat of a deep thinking thing, and like maybe let me not say that. Let me just simply say that I want to have this arrow, and I gave you two arrows which are pointing in the same direction. Now, no matter how you add them, no matter so what are we doing by xa plus yb? So xa plus yb, it means that you are just adding these vectors by shrinking or enlarging them. So this linear combination process, all it is doing, if we had like two vectors, A and B, and let's say we have a third vector, Q. Let me separate this so that you don't get confused. Okay. So if you want to write Q in terms of A and B, all I'm doing is I'm taking some direction of B and I'm scaling it. So this is my Y times B. I'm scaling it somehow. And I'm taking some X times A, such that when you add these two vectors, you add X times A plus Y times B. And again, you haven't learned this in the course and you will learn it later. But the point is, like, if you add vector, you just complete this square or this parallelogram, and the diagonal gives you the result of addition. Again, you don't need to know that, but I'm just telling you that if you have two vectors which are pointing in different directions, you can combine them by stretching them, thinning them, like shortening them, lengthening them. You can add them to create any vector. But when you can't do it, as Akshaya pointed out, like when are the situations you can't do it? Those are the situations if I give you two vectors which are pointing in the same direction. No matter how much do you shrink them, how much do you extend them, the result will always lie in this direction. It can never go out of this direction. So in this condition, you cannot solve your equation. So you cannot create this qubit. This is like saying if I come and give you 2, 0, and 0, and I ask you give me 0 plus 1, you can't do it, right? Like no matter how much you do like stuff with 0, like you don't have another one, so you can't do it. So you need 2 different directions to write any vector in a plane. Okay, cool. That was a good question, deep question. Think about it. You will get it. I'm sorry, I'm running slightly short on time. But as I said, we have solved 3 problems. Now only 1 more is left. I'm sorry, I'm not discussing optional problems. If you have time, you can stick around. Kylie, I already told her that like she can probably go at 5 if she needs to, and so no worries about that. So okay, so problem 4. Problem 4. So linear combinations we have discussed. Okay, so just to recall, inner product is projection. It's a measurement. It's a length. And I told you how to do it, right? And then linear combination is superposition. You have 2 qubits, you want to create superposition. That's second concept. And there was another concept which was about orthogonal vectors or orthogonal qubits. That just means that inner product is 0. So that's the third concept. So first and second problems, their concepts were related. Third problem, different concept. Now another concept. It's concept of matrix operations. So let's look at that. And somebody asked this problem as well, so we'll do it. But let's see what do we mean by matrix multiplication and why do we need to come up with it. So okay, so matrix multiplication. I'm sorry, as I said, I might take like 5 more minutes. It's not as bad as last time. Last time I had to go like half an hour, but matrix multiplication. Okay, why do we need that? And how does it work? So again, I'm not proving all these things to you. Like, how, for example, how do I know that inner product is that multiplication thingy? I will not prove to you how matrix multiplication works, although all this can be done. But I encourage you to think of them as a physical object, as a physical thing, as a real thing which happens. And then I told you a mathematical method of how to do it. And at some point you will make a connection, like later in your life, or when you are sitting and drinking coffee or something. If you don't make it, that's fine. But I'm just telling you that if you just look at problems are just set of rules. And I don't want to finish at just set of rules and tell you to follow them, and that happens. Think of it as some physical picture. So let's look at this. What is matrix multiplication? Okay. So I already told you that, like, if you were in last session, or generally if you know what vectors are or what qubits are, like let's call it qubit, why not? So I have a qubit. Now imagine all my computer could do is to store these qubits. So if you are like listening to this on a computer, imagine your computer just having a hard drive. No games, no painting software or whatever, nothing you can do, it's just like bunch of, drives where you just store these vectors, or and you just read them or something. It will be kind of boring, right? So you want to do things with them. So what does matrix do? So it does do things to vectors. Okay, that's probably let me write some more formal language. Matrix operates on vector. It's like matrix is a doctor or something. Matrix operates on vectors. And it's a mathematical concept. So it's an abstract concept. So you have a vector, and if you want to do something with it, so let's call some matrix do something. And what you do is you take this matrix and you apply it on this vector. So this will give you some other qubit. So let's call it Q1 or Q initial. You started from this Q initial. And you get finally Q final. So Q initial, do something, and then Q final. Okay. So what is matrix? Matrix is operation on vector. We'll repeat it a few times. What is matrix? Matrix is operation on vector. Matrix is, you all say, operation on vectors. Okay, cool, good. So, and I'm somewhat surprised that there is no homework problem for this. I mean, there should be one. But I guess, you all did it in lab. So just like to refresh your memory, if you have a matrix like 3, 1, 5, 7, and you have some vector, let's call it 1, 2. Yeah, then how do you operate? So these are rules, again, like I haven't justified to you, but these are rules, and just remember those rules, but know what it is doing. It is doing something to your vector. It's giving you a new vector. So I told you matrix does something to this initial qubit, and it's going to give you a final qubit. So the final result, even if you don't know anything, you know that it's going to be a vector without doing anything. So, and the way we do it is, just remember it graphically. Let me use a different color. I have been using very little colors here, but anyway, so you do 3 times 1. Let me expand this guy so that I can write all of that. I wanted black, but anyways. So you multiply first element with the first element of vector, then second element of row with second element of vector, and you write them down. This is not asked, but I'm just telling you, like, I'm just surprised why it's not asked. But anyways, 3 times 1 plus 1 times 2. Similarly, do the other one. The other one, you go 5 times 1, 7 times 2. If you don't understand, just watch your labs again. There will be recordings, no problem. So 5 times 1, 7 times 2. What does this gives you? 3 plus 2, 5. 5 plus 14, 19. Again, I'm somewhat fast, but don't worry about it. What I'm telling you, you start with a vector, matrix does something to that vector and gives you a new vector. So this is your new guy, right? Like new qubit. Okay. So, but why do we need to multiply matrices, right? I mean, like, what is matrix multiplication? Okay, so let's look at that. So I start with some qubit, let's call it Q1. I apply some matrix called M1 to it, or quantum gates. Think of it as gates. So let's change the letter then. Let's call it gate 1. So you apply some gate 1 to it, and you got some another qubit. Let's say this is, let's say, your Q2. It's rotated and shrunk. So matrix, as I said, if you give it a vector, what it will do? It will stretch it. It will either maybe shrink it. It will probably rotate it. These are the things you can do with vectors. So gate 1 does something like that. And then you apply some another gate, let's say gate G2 on Q2, and then you get some sort of Q3, let's say. It's a new qubit, right? Imagine, like, if you just had a computer which does only one thing, that would be kind of boring, right? Like if you are having a computer which does only one thing, not cool, right? You want to do more things. So you want to have, one G1, and then, you want to do something else, G2, and get the final result. How does this thing work out? So Q1 is where you start. The second guy, Q2, is some gate applied to Q1. Now, what is the third guy? Q3 is some gate G2 applied to Q2. But what is Q2? Just see here. G2 times G1 Q. So again, if somebody comes to you and they tell you, oh, I know I have a gate G1 which applies on Q1, I know what it does. I have a gate G2 which I apply on Q2, I know what it does. But can you give me a gate which let's call it G, let's just call it G. Can you give me a G which if I apply on Q1, I directly get Q3? Can you give me that? And to do that, as I said, like, it's like for physicists, it's hard. You need to think about all the things. But for mathematicians and like experts like you just do it on paper, kind of cool. So you say, oh, I just write it down. I start with Q1 and I know my G1, so I know how to get Q2. Then I know my G2, so I know how to get to Q3 from Q2. Then you just replace G2, Q2 from, basically you replace Q2 from here. And then you get Q3 is G2 times G1, Q1. So you come back to me, you're like, oh, if you know G2 and G1 and you know what kind of Q3 you want, all you need to do is G2, G1. Sorry, they're matrices. That's what you need to do. So this is where matrix multiplication comes in. So that's the mathematical. So now all the rules I will tell you, again, they are just rules, follow them. You can think about it. Sometime, like if you are free and, you are not bothered about exams or anything, you just try to think how it works like that. But for now, just take it from me. But this is what it means, that this is why we do matrix multiplication, because we want to apply something multiple times. Okay, so now let's look at rules. Sorry, it's already 7 minutes, but I'll finish. Yeah, I'll finish very quickly. It's done almost. So as I said, problems are easy, you know, like you just need to like see what's happening. So let's look at rules now. So let's do the last one, which our friend asked. So our friend asked this one, which is number 17, if I'm not wrong. Let me check. So our friend asked us, actually 10. Yeah, I think he asked us 10. Okay, so let's look at 10. So evaluate this expression. So let's write it down. So we are doing problem number 10, all of you. Please notice. Minus 2694. So that's my, gate 1. And then my gate 2 is 33 minus 51. And then somebody asked me that they gave me these 2 gates and they came to me and say, you know what, I have a qubit, I can use this gate, I know what I get. I have this gate and I know what I get. And what if I want to go from first qubit to the third qubit directly? Like, what kind of gate do I need to build? You're like, okay, I'll tell you. So and how do you tell him? You do matrix multiplication. So again, in the labs, there is a general formula. I don't like those formulas because there are a lot of indices like A11, B11, A12, like you get confused. I like to look at them graphically, and that's how I hope I can help you with that. So remember, the rule here is row by column. Row gets multiplied with column. So if you remember that, that will help you. And don't worry, this is new. When I first learned it in high school, I was like, what the hell is happening? So don't worry. So you start with row, you pick your row. This is your row. And then you pick a column. So you pick this column. So this will give you your first guy. This will give you your first element here. So let's do that. So I already showed you. So I'm going to go to black. So minus 2 times 3. So this is multiplying vectors. You see, like do you remember? Like this is like matrix applying on vectors. So there is a hint, some hint for you there, if you want to think deeply about these things. But anyways, so minus 2 times 3 is minus 6. 6 times minus 5 is minus 30. But let me just write it down so that 6 times minus 5 minus 2 times 3. Okay, so we got this one. We got first guy. Now what about the second guy? So second guy, let's go to a different color. Second guy will be, it will be a shade of red. So for second guy, we again do the same thing. We take first row and second column now. So by the way, you see this row and column notation. So this row and column. So this element is called, like if this is a matrix M, then it's M11. So this one represents row and this represents column. So if I take row 1 multiplied by column 1, I get M11. So this is M12. So how do you get it? You take row 1, right? Row 1 and column 2. Column 2. So you take column 2, row 1, then you multiply. And what do you get here? So you get minus 2 times 3, then plus 6 times 1. Okay. Then again, this is M21, which is row 2, column 1. So it's already telling you what to do. So, okay, so different color again. We'll see if we run out of colors. So row 2, column 1. Okay, let's do that. So go back to black again. Yes. So row 2, column 1. So 9 times 3 plus 4 times minus 5. Okay. And then finally M22. So row 2, column 2. Again, if it's too much, it's okay, because it is too much, but then it's just a rule. It's just mechanical rule. You remember this, you will be able to solve all the problems. No problem. Just take care of sign. That's the one mistake everyone makes. I do it too. So okay. We didn't run out of color. Good. Blue. So row 2, column 2. Okay, write it down. Black again. Cool. So 9 times 3 plus 4 times 1. Okay, so what does this give us? So let's write it down, So this time, if you have notebooks, please just do it with me, but I just write down one number. 3 times minus 2 is minus 6. 6 times minus 5. Okay, let me be slow. So minus 6 and plus minus 30. Here, what do we get? Minus 6 plus 6. What do we get here? 27 plus minus 20. Okay, let me say it again. Minus 2 times 3 is 6. Plus 6 times minus 5 is minus 30. Minus 2 times 3 is minus 6. 6 times 1 is 6. 9 times 3 is 27. 4 times minus 5 is 20. 9 times 3 is 27. And 4 times 1 is 4. So what do we get? So just do it. I hope I'm correct. Like if I made a mistake, please correct me later. So minus 30 plus minus 6 is minus 36. Minus 6 plus 6 is 0. 27 minus 20 is 7. 27 plus 4 is 31. I hope there is an answer which looks like that. Yes, this guy. C, right? Yeah, so we got our answers here. I will open the chat. I will ask you guys to speak if there are any questions on matrix multiplication. So let's start. I'll tell you, like, if you guys stick around, I'll tell you how this thing was invented and, why this is called algebra. But anyways, I mean, I don't know if I'll get time. So why is my brain freezing? Okay, chat. Okay, so chat here. So everyone publicly. Okay, so you guys can chat and like ask questions here. If you want to speak, I'll ask you to unmute and then you can speak as well. So I'll look for raised hands. Please type questions if you want to. Matrix multiplication. Questions on matrix multiplications, please. Questions on matrix multiplication, please. Questions on matrix multiplications, please. I hope I'm not offline. Can you guys hear me and like write stuff here? I see no raised hands. I see no questions. Thumbs. Okay, cool. No questions here, I guess. Oh yeah, it was Anthony. So yeah, that was your answer, my friend. So yeah, cool. I guess there are no confusions here. That's good. Okay, more chats. Okay, cool. Yeah, simple stuff, right? So, but again, all these things are abstract. By abstract, I mean, think of them as something in your head, not something on paper. I mean, yeah, there is something on paper, how to do it, but they also exist in, like your head. So that's the thing. And a cool fact is that, fun fact or whatever, that all this field is called linear algebra. So where does this word come from, right? Algebra is basically, I have this book open with me actually, where this comes from. So you guys can see. So this is a book by a guy in present day Iraq. His name was Muhammad ibn Musa bin al-Khwarizmi. I remember al-Khwarizmi. So al-Khwarizmi wrote this book in around 800 AD. So this was around 800 Common Era. Somewhere close. I don't remember the exact year. And the dude's name was al-Khwarizmi. So he was the first one. So if you had difficulty in your middle school, multiplying xy times, y cubed and, like doing like all sorts of things like z to the power 4, you can blame this guy for it because he was the first one who thought of expressing numbers as variables. Well, I don't know if it was exactly the first one. Different cultures, Babylonian culture, Indian culture, Sumerian culture, Greek culture, they all had some ideas here and there. But the name algebra and all this business of, writing things in X and Y and, A and B is attributed to this guy usually. And the name comes from a book. That book is called Kitab-e-Mustafa Al-Jabr Wale Muqabla. So I won't write the whole thing, but like the way I know it is Al-Jabr Muqabla. Wikipedia says that they don't know the translation of this, which is weird because, I mean, I'm not an Arabic guy, but like in India, the way we have some words, this means a tough competition or something. So, I mean, if you felt difficult things in school. That's why I remember it, because it was a fun fact to me that, all these, like when I was in 6th grade, 7th grade, and I was having headaches over, doing these things. The name of the book from which the name algebra comes from is from Algebra Mukabla, which means, tough competition. So, well, there is a secret behind linear part as well, but I leave it to you to find out maybe why it's linear, why all this algebra is linear, so I'll leave it to you. With that, I'm done here. Kylie has probably left. I hope she has left. In any case, so, okay, there are some people who know more than me. So as I said, different cultures have different mathematical facts, and you are right that there are other people. But the name algebra comes from that book. There is no disputing that fact. So yeah, there is no disputing that fact. And okay, so I will close the chat because it might get controversial. Actually, no. So any other questions? Any other questions on the homework, please? Any other questions on homework, please? So Kumar Hemant, I know, I know people get, offended about like stuff. That's fine. I'm just telling you that Brahmagupta definitely did work. There are people previous to him. There are people like Bhaskara, for example. And so he had some stuff. He had expressions for Taylor series. I'm just saying different cultures had different things. I'm just telling you where the name comes from, where the name algebra comes from. So that name comes from this book called Algebra Mukabla. That's all. Okay. So any other questions? On this homework, matrix, linear combination, vectors. Otherwise, we'll close this. I'm not doing advanced ones because they are somewhat difficult. Please ask them on Piazza if you have questions about them. And I think there are already some questions and already some answers on Piazza. So go back to Piazza. I don't see any chats. So I'm assuming everyone is fine and happy here. With that, goodbye. And yeah, I mean, I'll just highlight Kumar Hemant's comment in the sense that he is saying that there are some people in India who knew about representing stuff with letters for the first time, which I already said. As I said, this is not a new concept. Like people did it in different cultures, but the name algebra comes from this book. That was my only intention. Yeah, and history, we should like have fun with it. Like we don't need to like fight over who did this. I invented this. No, you invented this. It's good. We just have fun with linear algebra. Okay, great. But yeah, thanks for pointing it out, Kumar Hemant, and I'm grateful. And bye. Goodbye. If no other questions.